Hi, I am Geuorgui.
And I'm Jeremy Reisig, and this is our analysis for annular fin design.
The fin design is constrained to the subjective thermal condition of the system. Convection occurs at a rate of 60 watts per meter squared Kelvin from the air at an ambient temperature of 20 degrees Celsius. The cylindrical base, which needs to be cooled by the annular fin, is heated at 150 degrees Celsius. For the analysis, convection will be the only mode of heat transfer observed to the system. Different modes of cooling are to be compared through materials of copper alloy, aluminum alloy, and stainless steel. An optimum design will be used the least amount of fin length as a result of dissipating the heat to the ambient temperature with minimal amount of material. The geometry of an annular fin is composed of a rectangular cross-sectional area to be revolved around the neutral axis. By creating a revolved system, a cylindrical base is created which serves as a circular fin for cooling. For our initial design, a fin length of 1.25 meters and a thickness of 0.005 meters is used for the fin plate. To analyze the thermal solution, a mesh is created for the system. The fin is to be modeled as a geometry in 3 dimensions and will need mesh elements that reflect the analysis. To create this, the mesh method is changed to hex, dominant, and ANSYS. By doing this, an all quadrilateral element shape can be applied as an A-node brick. Additionally, the advanced sizing function is disabled so that an element size can be specified based on the geometry dimensions. Typical mesh sizes for the fin run between 5 to 10 millimeters, so that every portion of the fin can be effectively analyzed. To complete the setup for analysis, boundary conditions are applied as a steady-state thermal mode of analysis. The base of the structure is prescribed a temperature of 150 degrees Celsius. Additionally, convection is applied to the entire structure through application of the convective heat transfer coefficient and ambient air temperature. The modes are defined as a ramped input so that the steady-state cooling is observed in the solution. The initial parameters defined by the geometry and setup resulted in a close approximation to where the heat is fully dissipated. By general analysis, we can see that most of the cooling occurs within the first fifth of fin length. This geometry will be held constant for comparison to the other materials. At the same length, the aluminum alloy was able to dissipate all the heat to the surroundings. The minimum value denotes the computational point where the temperature first hits 20 degrees Celsius. This point is very close to the outer length, but will need mathematical modeling to find the exact point. By retaining the same geometry, results for stainless steel show that the minimum point for complete cooling is achieved at a much lesser geometry than that of the copper and aluminum alloys. Where copper and aluminum needed most of the length to achieve full cooling, stainless steel achieved this in approximately a quarter of the prescribed length. To find the exact solution, mathematical modeling is needed to redefine geometry. To begin the thermal analysis, fin assumptions for complete cooling are defined. For a fin tip condition of cooling to the ambient temperature, an infinite fin is used. From this, the temperature changes described by theta are driven to 0. By assuming the equation for the theta equivalent, a relation between temperature and length is found. In this instant, fin variable m is defined as equal to beta for the Bessel function. By using the thickness initially defined by the geometry, constant betas are found for each material. Finally, to complete the analysis, lengths in increments of 0.2 meters will be used.
Each material is then applied to the fin equation relating temperature and length. By solving for a constant beta, the equation can be inputted into Excel for data correlations. Initial analysis for the copper alloy is analyzed in increments of 0.2 meters until the solution converges to the exact ambient temperature. The same lengths are then applied to the other materials for comparison. The math model findings reinforce our initial ANSYS model approximations. By plotting the materials along the same distances, several patterns are found. Primarily, the stainless steel material has the fastest cooling length and will require the least amount of fin length. Secondly, like our ANSYS model showed, most of the cooling is achieved before 1 meter is reached. At this point, only decimal increments to the ambient temperature remain. The determination of the exact fin length allows for a redesign of the initial geometry per each material. For the copper material, a length of 4.2 meters is used. However, by applying this geometry, we can see that the point of convergence to the ambient temperature is very far away from the fin edge. This is ultimately due to the decimal approximations made in the math model. Unlike the copper alloy redesign, the aluminum alloy geometry change resulted in a nearly exact approximation. The retooled fin length for 3 meters matches the math model approximation for convergence. Final design for the stainless steel fin is redesigned to a fin length of 0.8 meters. Oppositely to the copper model, the quicker cooling rate shows inaccuracy in the fin length. Cooling is achieved at an inner diameter much less than the math exact fin length. Better approximations to the ANSYS convergence points are to be determined by the relative error between the two models. Overall, the exact solution difference can be found by relating the solution points. For all three materials, error was higher than 60%. These high errors can again be equated to the decimal approximations. While the math model goal was to seek the exact point of the solution, ANSYS convergence occurred at a much lower decimal range. By approximating convergence at 10% to the final solution of the math model, better length equivalencies are found. The relative error for each material is found at a 10% convergence rate. Based on this analysis, for a better approximation to ANSYS, the error ranges are found to be much lower. Cooling is While the math model and ANSYS solutions may yield to higher error ranges, convergence approximations show that the model geometry is a good fit of analysis. The best result of the two models combined are optimized by using stainless steel materials at a length of 0.35 meters. Final considerations for a greater optimal solution could involve change the base diameter geometry or the fin thickness.